j'ai le grand privilège d'introduire et d'accueillir Tiffany Timbers, qui est professeure adjointe à l'Université de la Colombie-Britannique à Vancouver, option enseignement. So Tiffany is an assistant professor teaching stream at UBC, and she is the co-director of the Master of Data Science program. And so in this role, she does a lot of teaching. She has a PhD in neuroscience with 2 postdoc, and she's been instrumental in spearheading the data science program, has 2 books, and is a leading figure for reproducibility and data science. So thanks a lot, Tiffany, for accepting our invitation. I'm looking forward to your talk on Opinionated practice for teaching reproducibility. The floor is yours. And for the participant, if you want to ask questions, please wait until the end, and then I'll also monitor the chat if there's something. Thanks.
Wonderful. Thank you so much, Leo, for the introduction, the very kind introduction, and thank you very much for inviting me to come and speak. It's really nice to meet everybody here. I wish it could be in person, but things are as they are, and we'll make the best of the current situation. And yeah, I think we're all, pretty practiced at Zoom at this point, so we can make this really fun and interesting, I hope. So I'm going to paste the link to the talk slides in the chat in case anybody is interested in accessing them, because I've kind of shared a bunch of links that are relevant to the topics that I'll be covering in the slides. So you don't have to feel like you have to write anything down. They're available to you there. So yeah, let's get started. So I'm going to start off talking a little bit about me, not too much, more focused on what I teach at UBC to help provide some context for the talk that I'm going to give today. So I have teaching experience formally at the university and also less formally or different type of formally outside the university through various kind of volunteer organizations. So I've been an instructor, a certified instructor for both software and data carpentry. And so these are not for profit kind of now international organizations that provide 3-day workshops to graduate students, postdocs, and faculty to get them up and running using computational skills to improve the efficiency of their research. And this was kind of like where I first started teaching these topics. I'm also an RStudio Tidyverse instructor. And so that's my experience outside of the university. And then with the university, I have worked as a teaching postdoc here at UBC, and then moved into a role of being an assistant professor of teaching in the Department of Statistics. And when I moved into that role very soon after, I became the co-director of the UBC Master Data Science program. So I would say like 80% of my teaching falls in the Master Data Science program, and I spend 20% of my teaching in the undergraduate space. And so that means about 1 undergraduate course a year is what I have experience with. So for graduate courses, I teach programs that span from programming with R to introductory statistics, and then reproducibility and collaborative software development. And in the undergraduate space, I've developed and taught an introduction to data science course. So this is for first-year students who have no previous computing skills, or at least it's not required. And for that, there are some very, introductory reproducibility topics that are covered. So using code to do analysis is one of them. And then the second was that we give a very light 1-week introduction to version control. And then I'm currently developing a new course for undergraduates that will be part of our new data science minor, which is reproducible and trustworthy workflows for data science. And so this one is going to focus a lot on reproducibility and bring some of the topics that we've been teaching at the master's level into the undergraduate space. So I'm really excited about this course, and giving this talk has really given me a chance to reflect academically on what's going to go into that course and how I've taught these things in the past in the Master of Data Science program. And hopefully I can iterate on both of these things in the next year and improve them further. So before we get started in talking about reproducibility and data science and how we teach it, I think it's important that we take some time to define data science. And so the definition of data science that we adopt at the University of British Columbia is the study, development, and practice of reproducible and audible processes to obtain insight from data. So you're answering a question to create some sort of insight with the data, but how you do it is also important. It's important that it's done in a reproducible way, we think, and that it's audible or transparent, okay? So there's some record of how it was done. So to use that definition of data science and the emphasis I've just placed at the end of it, I think it's important to also define reproducible analysis and audible or transparent analysis. So reproducible analysis, we adopt the definition given by the National Academies of Sciences, which is reaching the same result given the same input, computational methods, and conditions. So the input is the data. The computational methods would be like the code, the R code or the Python code you use to do the analysis. And then the conditions are basically the computational environment on the computer you use to do it. Okay, so the version of R or Python, those packages that you use, the specific versions of those, and any operating system dependencies. And a transparent analysis is one where you have a readable record of the steps that were used to carry out an analysis. This is most easily made possible by using code to do your analysis, as well as a record of how the analysis methods evolved over time, because as you all know, data analyses are not just done in a minute. They're usually done in days, weeks, months, sometimes years. And so things change throughout this process. And so we think it's really important that you both have a record of what is the final sold product, whether it's going into publication or into use in business, as well as how that changed over time. So why do we adopt this particular definition of data science? Well, we think data science work should bring both insights, which should answer a question, and employ these reproducible and transparent methods so that you can make trustworthy results and data products, whether it's an academic paper, a dashboard that's deployed at a company, a software package that's being used for prediction on the web. You want to have trust that what you think the data analysis is doing is it's actually doing. And you can build these kinds of data products using non-reproducible or non-transparent methods, but we lack confidence, I think, in how these data products or results are created. And we think this comes from lacking evidence that the results or the product could be regenerated if you gave the same input, the same computational methods or conditions. We think it lacks evidence of the steps taken during creation. So if you're not sure how it was made, it's hard to trust it. And then without that kind of history of the project and a record of it, it's hard to know why certain analysis decisions were made to create the product or the results, and that could lead to a lack of trust. And then if you think about the analyst and their experience, there's other reasons why we would want to adopt this a definition of data science that in particular requires the use of reproducible methods. So these are some things that can happen to you as a data scientist. So you could create some interesting results, or you could generate some interesting results, but maybe you can't regenerate them. So there's some past version of your work that generated these interesting results, and the current version doesn't generate them, and you're not really sure why. The second one's not necessarily related to, it's more of maybe collaboration, but it still ties into the reproducibility tools. So sometimes your email inbox becomes full of information related onto the project that only you have access to and not the entire team. So some tools to make sure that everyone has access is really important and can cause you a lot of stress and problems if that's not the case. Non-reproducible and non-transparent tools can lead to a lot of loss of time when you need to rerun your analysis, especially if you made a small change, but there are some upstream processes that take a really long time to run. And then I think 4 is a really big one that's sometimes underappreciated, is that the activation time to becoming productive after you take a break from a project. And we all take breaks from a project, right? Especially in academia, you submit a paper and you walk away and you wait for a few months to get the reviews back, and then you have to make changes. And to start to initiate those changes again, you have to dust off that old project, remember how to recreate it and rerun everything. And that can take a long time if you're not using transparent and reproducible tools. And then finally, the 5th one is perhaps one of the saddest ones of all, is that you have that problem where you have code that only works on your computer. And it's a really challenging problem because you can create these great and interesting results on your computer, but you can't really share them in a reproducible way with other people. And so it's very stressful because you wonder if they're true, if you can only generate them on this one machine, but they must be true because they can be generated on this one machine, and it can be very stressful. So hopefully with the last couple of slides, I've convinced you that reproducibility is really important for data science and should be part of the definition for data science. So why is it so hard to teach it? And I don't have hard data that it's hard to teach it. I just have more of my own experience of teaching courses that are about reproducibility versus courses that are about, statistics or involve, machine learning or programming. Data science students really see the value of those things because they hear about them in the, I'd say like in the general public, we discuss the value of AI and machine learning and statistics and data and coding is cool in the tech industry. Reproducibility doesn't have that same sort of public appreciation for its importance, yet I think it's equally important for creating data science analyses that are trustworthy. So students tend to not be as excited to be in those courses that have reproducibility in the title or workflows in the title. You can read it through if you ever do surveys or through the teaching evaluations. At the end of the course, I think, I hear, at least from some students, that they learned a lot, but it's almost always prefaced with some sort of but. It's like, this course was more useful than I thought it was going to be. And so I do think that it is harder to teach for a variety of reasons that I will go through and expand on later, more in this talk. So some of the possibilities, one I've just kind of gone into a little bit, is a lack of awareness of the problem. And then the second two I've kind of hinted at as well, but I think I can spend another minute about, is that reproducibility seems to students to be, once they learn about it, an inconvenient means to an end rather than an important skill. In particular, number three maybe really hits in it, in that reproducibility itself doesn't lead to any novel insights, not like statistical analysis might or machine learning. And so I think that there may be more things, but these might be some of the key things as to what makes it really challenging to get student buy-in to this topic. And you need that student motivation and buy-in, I think, for learning to happen. So through our experience teaching these courses in the Master of Data Science program, so we have, I'd say, like 3 courses that are really focused on this. And then in the little bit of experience that we have in the undergraduate space so far, we think that there are 3 key things for teaching reproducibility. There's probably more than 3 things, but we think these are the top 3 things. So one is placing extra emphasis on motivation. So motivation is important for any kind of learning. Many people in this talk, listening to this talk today, probably have experience teaching, and you probably, yeah, of course, it's motivation. But I think this requires extra motivation, and on top of other topics that you might have experience teaching. The second is that I think guided instruction is really important, and I'll elaborate what I mean by that later in the talk. And then third, lots of practice. And again, for the teachers in the room, lots of practice, you're like, yes, of course, practice. But I mean, the lots of and the 3 exclamation marks at the end, I think, is what I'm trying to emphasize here, is that it needs extra of this stuff. So I'm going to break this talk up into kind of 3 sections to address each of these kind of like key issues, and then hopefully convince you that they are a key issue, and then provide some examples of things we're doing to address these key issues. So why do we need extra motivation? So Git is version control software, probably the most popular version control software in the world right now. And it's really hard to use. It's hard to teach. So here's a really famous XKCD comic where the one person at the computer is saying, this is Git. It tracks collaborative work on projects through a beautiful distributed graph theory tree model. And the second person behind the computer says, cool, how do we use it? And then the person at the computer says, no idea. Just memorize these shell commands, type them in to sync up. If you get errors, save your work elsewhere, delete the project, and download a fresh copy. And this is like not, this is, I'll show you in a slide or two, that this is like a legit strategy put forward by Git educators, because it is, it's a very powerful tool, but it's a complicated tool and difficult. It takes a lot of time to learn. And I would say, like, most data science data scientists don't even come close to mastering this tool, right? Like myself, I'm still like probably some sort of intermediate level Git user. So here's a legit example for those of you folks who haven't taught this or used this yourself of why Git can seem hard. So what we're trying to do here in this command that you might put in the command line is you want to check out your work 2 versions ago, okay? So we're trying to, this is the command to look at your work from 2 versions ago. Git checkout head ~2. And this is the output that you get from this. there's a very alarming thing for a novice Git user that's coming out in the second sentence. You're in a detached head state. Not only is that like has no kind of like really immediate meaning to what's going on computationally, like a detached head is like a very alarming thing to a human being. And then the next sentence is you can look around, make experimental changes and commit them. You can discard things. It won't impact branches. And you're like, I don't even know what a branch is. So this very common reproducibility tool is like not easy to use. And this kind of loops back to the original XKCD comic that Jenny Bryan, one of the leading educators in version control in the world, sent out this tweet in 2016 when she was preparing to teach Git at UseR, that she planned on teaching that, burn it all down strategy is a viable Git strategy, because sometimes things just get too complicated and it's not worth your further effort trying to figure out how to get yourself unstuck from whatever mess you've got yourself into. Okay, so one of the most common tools is hard. I think another tool that is used a lot in the beginner classroom for reproducibility and used quite widely for reproducibility is our markdown. And our markdown is pretty, I would say, yes, introduce it to new learners. It's not at the level of Git, but when you start to need to export to PDF from our markdown, then you have to bring in the beast of LaTeX. And for those of you who've had experience with LaTeX, it is also quite complicated software. And our markdown tries to hide that from you, but the error messages that you get from that end up being some sort of version of a LaTeX error. And so there is this learning curve that's difficult and like might put off new students of learning this. So here's an example of a very simple R markdown document that we're trying to convert to PDF, and we've made a mistake. We've used a special reserved math word, \gamma, outside of $signs. So it's not within a mathematical equation. And then you get a very big red error message, missing inserted $signs. If you weren't even thinking about or had no knowledge yet of using mathematics in your LaTeX document, and you just happen to accidentally use this word and use the word gamma and accidentally put a slash in front of it, you would get this message. And it's, eventually you could maybe parse it. There's some hint about what's going on, but it's still quite a bit of I think, a barrier or a turnoff to using this tool. And then, in addition to things being challenging, I think that reproducibility tools can also be very different from code in that they can be really slow. So Docker is a tool that's useful for sharing computational environments. And to create what's called a Docker image or a Docker container, you need to basically come up with a set of installation instructions. Those installation instructions are written in Linux, and installing anything, as we've all experienced on our own laptops, is a slow process. And so here is an example of a Docker file that uses a very common R base image and then adds 3 R packages to it. And so once you have this, it's really great for reproducibility because you can share it with other people and they have the same version of R as you and the same version of those packages. But creating the environment to share and distribute with others with this is quite a slow process. So here on my MacBook Pro with 16 gigabytes of RAM, this took me about 5 minutes. And that was without running into an error and me knowing what I'm doing, right? And that's just like running one command. So you can imagine that a novice that's, learning how to use apt-get because they're on a Mac or a Windows machine and they've never experienced installing things with with Linux, that they are not as familiar with the shell, they make mistakes. This is going to be really difficult for them to learn. So hopefully what I've illustrated with these 3 examples is that reproducibility tools are sometimes difficult to learn and challenging to stick through. They really help your analysis, but it's kind of like training for a marathon, right? It takes a lot of like looking ahead and keeping your eye on the prize and not giving up. And so I think because of that, we need this extra motivation for teaching these tools. So how do we provide this extra motivation at UBC when we teach these courses? Well, one thing we do is tell stories from the trenches, and those are stories from the instructors, so experiences that we've had when we have failed to use reproducibility and like what the repercussions have been. The second is studying case failures that have bigger real world consequences. And then third is letting students fail, but doing it in a controlled manner. So I'm going to give examples of each of these now. So here's 3 stories telling from the trenches. I won't read them all out. I'll perhaps just read the second one out here. And then the rest are in the slides if you're interested in reading some more or using some in your classroom. So this one's about me. As a master's student, before I embraced data science techniques, I spent many hours customizing the figures, the colors of a figure that had many points and lines using Adobe Illustrator. And the next week, in a meeting with my supervisor, she very correctly pointed out to me that the color scheme I chose would be problematic for people with color blindness. Then I had to spend many more hours repeating the same work to change the colors of all of the lines and points to fix it. It was a very frustrating experience to repeat such tedious and time-consuming work. And then that caused me to be delayed on other deadlines because I had to spend my time redoing this thing that I thought I was already done. So if we can tell stories like this to students in the classroom, we can illustrate like a very real problem that they could encounter if they used a non-reproducible tool. A reproducible tool like ggplot with R, this would have taken me like a minute or 2 to solve, as opposed to hours to solve. So that's could help create some real buy-in from students. I think also having the instructors tell them about problems that they've faced in their own work really humanizes this as well, because this is not, students can imagine themselves having to create a figure for some reason in a presentation, in some sort of like report that's, going up the food chain in their workplace, and not necessarily thinking about like an academic paper or a book or something that maybe they will never write, get the experience writing, depending where their career path takes them. So I think that providing these stories from the trenches really helps motivation for those 2 aspects. However, like what were the real world consequences there? I missed a couple deadlines. I, wasted some time. It's not maybe scary enough to scare them into reproducibility. So maybe scary is not the right word, but I think it's also worthwhile to bring to the attention of students of cases where there's been bigger consequences in the world to really make them think about the impact of reproducibility on data science. So this is something that we're starting to do that's kind of newer to us at UBC. And so we're just building up a list of cases at this point, but I plan to include them in my course in January. And in particular, some of these consequences have been quite important. So in this last study, or this last case at the very bottom of this table, the consequence, the data science non-reproducibility issue led to a real world consequence in the delay in the opening of a hospital. And so that's something like that nobody would really want to see, right? And so hopefully when we share these like impactful real world consequences, it helps motivate them to want to push through learning these hard tools and these tools that take more effort to use. And then the third thing that we do to induce motivation is there's nothing more powerful for your memory than having a really emotional experience, right? And a really emotional, frustrating experience with your own work, with reproducibility, is quite impactful. And I mean, I certainly had quite a few of those in my graduate career, which has made me so passionate about this topic. And I think why I spend so much time talking about it nowadays. But I mean, it took me a long time. I don't think it should take everyone a long time. I don't think I'm alone in that thinking. And I'll talk about another data science figure who also argues that it shouldn't take that long of a time. So can we create an emotionally salient, frustrating experience for students, but in a shorter time span? So this is an exercise that we use in the classroom in the Master of Data Science program, which has come from inspiration of a similar exercise that Jenny Bryan used at UBC when she taught Stat 5 for 5. And I've just modified it a bit to work to make it a little bit more scalable for the larger classroom. So what we do is we give students a GitHub repository, and in the Master Data Science program, they've already learned how to use GitHub. And so in this GitHub repository, when we give it to them, we say, we want you to make this work on your computer, run this analysis. And so they have to clone the GitHub repository, which they know how to do. They read the README, which tells them very explicitly how to run it. But what we have omitted in this GitHub repository README is a shareable computational environment and a listing of all the dependencies of the packages that they would need to run it. And what we've also done is injected some quite obscure R packages so that, that they probably don't have on their machine, so that they will go through that experience of not being able to run the analysis without putting some effort. And then if you really want to kind of up the game, you could put in some absolute file path that might only work on your computer and not the student's computer. And you ask them to make it work. And you'll let them struggle, maybe 15, 20 minutes, and they, get the message from R when they try to run the analysis that they're missing some, either the cow plot package or the egg package, and they have to install that. And then maybe if you did include an absolute path, that file doesn't exist on their computer, but they can see it in a repository, and they have to dig through the code and change the file path. And that creates, I think, a good emotional, like a positively negative emotional experience that's like contained to a short amount of time. That's like, this is difficult to try and run code like this. And then in the same classroom experience, you give them a second GitHub repository. And in this one, you've shared with that GitHub repository a shareable computational environment. We use Docker. And in that README, it gives instructions on how to run it. And then the students will hopefully experience that it takes them, just a few minutes to make that project running, and they don't have to do anything other than follow the instructions. And so like, hopefully that, powerful experience of having something really not work and then something work really easily will help motivate them enough to stick through learning a complex tool like Docker. Okay. So what I'm going to move on to now is the second thing that we think is important for teaching data science, and that is why guided instruction. So from our experience at UBC, reproducibility is not something that most people or students figure out on their own, or if they do, it's not an efficient process. It's like some wandering path. And I think Roger Peng from Johns Hopkins University says it so well in his blog, in one of his blog posts. He says there is no need for a new data analyst to learn about reproducibility from experience. We don't need to lead a junior data analyst down a months-long winding path of non-reproducible analyses until they are finally bitten by the non-reproducibility and therefore learn their lesson. We can just tell them, in the past, we found it useful to make our data analyses reproducible. Here's a workflow to guide you in your own analyses. And then within that one statement, we can compress over 20 years of experience. I really love this excerpt from his blog because it just, I think, speaks so clearly and truly to kind of like what our role should be when we're teaching data science to students. We don't have to let this happen to them. And we've probably gone through these experiences, and I can say I certainly have. And I don't want my students to, kind of follow that part of my learning experience. So here are 3 examples that we use for guided instruction in our UBC courses. One are pre-lecture activities. The second are live demonstration. And the third are guided worksheets. So I'm going to talk a little bit in detail about each of them. And there's just one note that in these 3 things that we use, we've created a lot of our own resources. And I think that happens quite often in data science and reproducibility because things change so quickly. But that also means that you have to kind of buy into the fact that you're going to have some constant curation that's going on. So one example is last year, GitHub, midway through term 1, switched from calling all their repositories default branch from master to main. And that causes everybody who's been teaching this for a long time, or even that year, to update all your notes has to be gone from master to main. Some of the software tools and projects or demos you've had might just break and not work anymore. And so it's just something that is really important if you're teaching this to kind of be very aware of and just kind of buy in that this is something you're going to have to deal with. So this is something we dealt with last year, and it was around that is under the topic of version control, but we went through and updated most of what we're doing now. But what I'm going to use is this topic of version control to show you the 3 different ways that we would use guided instruction to teach this topic. So this example is coming from Data Science 100, which is an introduction to data science course, and we spend again 1 week teaching version control. So what we do is before they come to class, their pre-lecture activity is to read a chapter in a book we've written about version control. And it starts out quite conceptual. It goes through some worked examples, but it gets the students thinking about the big picture of this and hopefully generating questions from reading it, because we don't expect, just after reading a chapter about anything in a book that you'll have a full understanding. Then in the classroom, this year it was the Zoom classroom, but we also would do this in the in-person classroom, we go through a live demonstration. And the live demonstration not only includes, say, the coding aspect of any data science topic and under reproducibility, but also using graphical user interfaces like the GitHub web app, for example, or the RStudio app or the Jupyter app, for example. And we think this is really important for a couple different reasons. So one is that there is at least some evidence in the pedagogical literature that things like live coding is really useful for teaching programming and anything in computational methods related to that. And just because you are not, programming when you're using all aspects of version control, like this graphical user interface, doesn't mean that it isn't beneficial to have somebody kind of show you how it's done, show you common errors you might make, watch the instructor make errors, and then be like, oops, I made that error, and turn that into a teachable moment. So I think it is really worthwhile that even when you step outside of the coding landscape of reproducible tools into graphical user interfaces, to not just assume that students can figure it out from their own. Some of these data science graphical user interfaces are overwhelming. I don't know if anyone here has had any experience teaching the Amazon web services graphical user interface, but that is probably the most complicated thing I've seen in my life. And you certainly need to guide students through an experience like that. So we guide students through these experiences of using these graphical user interfaces, and we do it I would say in a very slow and pedantic way, because it's almost more challenging to give a live demonstration with this tool than it is to give a coding one, because as soon as you click that button, you're like swept off into a new page and they can't see what button you clicked. And sometimes there's like 3 or 4 things deep that you have to go through, and they're hard to go back one step. So you have to talk, you have to be slow, you have to be methodical, and students really value these, and recording it, whether you're in person or online, can be really helpful. So students can actually go back when they miss something, when you click on something. So yeah, live demonstration I think is really key here. And then, they've thought conceptually about it, they've generated some questions, they've watched you use the tool. Then I think it's really important that they go through and they use the tool, but they have some sort of scaffolding around how you direct them to use the tool. So we have these guided worksheets. For us in this course, they're Jupyter notebooks. They could be our markdown documents. You could create them with many different things. And we have it's a mix of some formatted text that has instructions. So here is step 3 or question 3, where they're creating and editing files on GitHub. We tell them explicitly what to do, what to name the file. And so they follow these instructions, and then we have some questions that they need to answer. And we use software through Jupyter that allows us to give them automated feedback to let them know if their answer is correct or not. And these questions can be about how would I say, operational or logistic steps that they just did to help, recall, but then they can also be conceptually about what was going on. So for example, this one is about commit messages and whether you need good commit messages. So the students just did a change on GitHub. To make that, to record that change, they had to associate a commit message with it. And then we had, 2 stages back in their learning commented about what's the role of commit messages and why they're important and why you write good ones. And this kind of links back that conceptual learning to the operational or mechanical thing that they're doing right here when they're using GitHub. So we think putting those 3 pieces of guided instruction together can be really beneficial to get students learning these challenging tools efficiently. Now, the last thing that we think is really critical, or at least in the top 3 for us for teaching reproducibility, is lots of practice. So why lots of practice? So mastery of a subject often involves consolidating ideas, concepts, and theories into long-term memory. And consolidating most things into long-term memory requires repetition. And again, to the educators in the room, this isn't new. You know that we have to practice things, we need to study things to do well in our tests, and so that we can use things outside of the classroom. But perhaps what might be new to some of you in here when thinking about teaching reproducibility is that we actually want the students to do more than just learn about reproducibility. We want them to do more than know what version control is. We actually want them to employ, use, and practice these things. We want to change their habits or behaviors. I think this is really kind of different or important, that you want to get these students to the point where this becomes their default. And so what exactly is habit formation formally? Well, it's the triggering of behavior from contextual cues. What would be contextual cues in the cases of reproducible research? Well, it would be the tasks in your brain you're thinking about that you need to do. So say, you need to share a file with a collaborator. What should your habit be for doing that? You need to record the history of your project. What should your habit be for doing that? So these are the kinds of things that I'm trying to think about here. So how does habit formation help? And I think I've hinted at this a little bit, but I'll explicitly address it here. I think what's really important is that from the habit literature, one of the interesting things is that habits protect individuals from motivational lapses, where a desired good behavior is not expressed due to a momentary lack of willpower. And there's, I think, two things that kind of really contribute to this for reproducibility. One is that non-reproducible workflows tend to be easier. If you're going into doing a writing project, a collaborative writing project, opening a Google Doc and starting it and adding your collaborators is easier than setting up an R Markdown document and setting up a GitHub repository and then adding your collaborators to the GitHub repository and everyone cloning a copy of the GitHub repository and then opening up the R Markdown document, right? So that happens. There's that easier aspect to these non-reproducible tools. And then life gets busy, and life has gotten really busy lately. Like, I think that's kind of the pandemic can maybe give us some insight into, or not insight, but make us appreciate more that when you get these added stresses in life and these added extras in life, that maybe all of us have started to see some of our good habits, things we want to be doing on a regular basis, kind of not do. And so you need to build strength and habits, I think, to protect against these things. So without reproducibility habits, it's a perfect storm for the non-reproducible alternative to be done by any of us, and especially by the students that have less experience, even when they know it's better or we know it's better. So we want to build these reproducibility habits up until a point where the students and ourselves opt to do this by default. Anytime you start a project, like if the reproducibility tool you've used for version control is Git and GitHub, you just open a GitHub repository, add your collaborators, start communicating through issues, as opposed to using some non-reproducible method like email and a Google Doc, for example. So if we want to form habits, reproducibility habits with our students, help them learn them, how do we do this? Well, habits are best created through frequent and regular and sustained cue exposure. So that's practice. And here's where the lots of practice come in, is that some studies have reported that the median for this is about 70 days before kind of reaching the habit plateau phase. Okay, so that's lots of experience. So that's putting this into months. That's two and a half, just under 2.5 months. Okay, so almost like a semester long course. So how do we embed lots of practice in our data science classrooms at the University of British Columbia? Well, we get students to do practice following the live demos. So we do, and then they do after us. We also have lots of low stakes assessments with small, short problems. So those guided worksheets that I showed in the last section is an example of that. And then the third one I think is really, really important and probably underappreciated, is that the learning technologies and platforms that we use are using authentic data science reproducibility tools. So I'll speak more on this in a minute. or actually right now. So in the Master of Data Science courses, so we have 21 credit courses that the students take. For each of those, they have 4 assessments. And we give them each of those assessments as a GitHub repository. So they have to go to GitHub to get their work. They have to somehow get it on their computer. They need to make changes and then send it back to GitHub for us to grade it. And we've added some extra requirements that they have to have 3 commits associated with each homework submission. So we have an automatic Python script that checks this and lets us know who doesn't do that, and then they lose some mechanics marks. So we give them 5% of their grade for each assessment is a mechanics grade, and really encourages them to do it. And basically, 95% of the students will do it in the first assessment, and then 100% of the students will do it afterwards, because it's, kind of like 5 bonus marks for them. But it creates this tremendous amount of practice that by the end of our program, they have version controlled their work in over 96 different repositories. And I'm saying over 96 because in some courses we have a few more assessments and we have a final project and those sorts of things. So here's just a snapshot from a home table from a UBC Master of Data Science student workspace. So on GitHub, we give them a repository that's kind of like their home repository that helps them track all of these things. And in these 4 columns here, and same thing on these side, each of those blue links is a different GitHub repository that they have access to where a different homework assessment is. And then we also use GitHub repositories to share our course materials with the students. So each of under here courses, these are all about the 20 courses that they would have access to those GitHub repositories to access their notes and the solutions and those sorts of things. So they really do get a lot of practice. So some things when you're giving a lot of practice are easier than others. Here I'm going to talk about what are some of the more challenging things. So sometimes in reproducibility topics that you're trying to teach, there has to be like 5 or 10 or 20 different kind of like simple to semi-complex steps that need to happen before you ever encounter this scenario that you're trying to teach. So one example I have here on the bottom is like performing a code review of a pull request, right? First, you have to have a GitHub repository. Somebody has to make a branch. Somebody has to make some proposed changes, and then they have to send that pull request. Oh, and somebody had to write code in the first place. So all that kind of has to happen before you ever get to practice doing a code review. And so it's hard to give lots of practice for something like this without kind of doing what I'd like to say is like some pre-baking. And so you can think about this as like, if you've ever watched a baking show, and here's Martha Stewart here, like a snapshot from her, that this is about how to make, I think it's angel food cake with like coconut icing. And so she's got a final product here to show you like, what are you working towards? And then I think she's at the stage in the video where she's going to be working on the icing. Okay, so the cake has been baked. You don't, she showed you how to do that a bit earlier in the video, but you didn't sit there and watch her bake the cake. She's like, and now we're going to move to the icing stage. I've already pre-baked this for you. And so she can talk about like the techniques and stuff that she's using to make this beautiful icing that you see on her final product. So we can do things like this in the data science classroom when we're teaching reproducibility, so that we kind of keep our students on task and get them to practice these more complex things. So it takes a bit of preparation as a instructor, but it's, once you've set up these exercises, and if you do them in a automated and reproducible way yourself, you can make it easy to reuse them from year to year. So I'll go back and I'll pick on this code review example again. So for this one, we have a GitHub repository, which uses, which we get the students to import, which is like make a copy of. And then we use GitHub Actions so that we tell them to do one specific event. And then it uses GitHub Actions to automatically generate a pull request from a GitHub bot. And then they just have that pull request to practice the review on. And, through this, you could set up a couple different versions of GitHub repositories with different aspects that you want them to focus on in code review, for example. So I'm just going to wrap up so that I leave some time for questions. So here are the 3 things that we think are key for teaching reproducibility. Again, it's not all of the things, but the 3 things that we think are, at least some of the most important. And so one is extra emphasis on motivation. The second is guided explicit instruction. And the third is lots and lots of practice. And one thing I do want to say is at this point, it's just like our opinion, but we do have some anecdotal evidence from our courses that suggests that, you know, this is effective. So in the very first year of the Master Data Science capstone projects, our projects had too much of what I'd like to call technical debt. And this, what does that mean exactly? Things that prevent other people from like taking the project further. So we didn't have shareable environments. We had version control, but it wasn't well organized. The file and directory structure wasn't as well organized. We taught these things, but we didn't do a good enough job reinforcing these things and assessing these things. So as our experience of teaching these things has improved, that we've seen a significant reduction in technical debt in these capstone projects. And we hear feedback from the capstone partners, which are external to UBC, from more and more of them, that they're able to continue these projects on. They're really useful. We get people coming back and so on. So that's really exciting. We've also gotten some positive feedback from alumni, some solicited and some unsolicited. And so, for example, they had one of the alumni came back from their company Git training, and they wanted to let us know that, you know, everything they learned in our classes was really important, and we taught them more than they got in their company training. So that's really great. And then one of those alumni thought that Git and Docker are and the strong focus on reproducibility are one of the best technical skills that the program offers. So what I'd like to do next with this is, you know, move away from this anecdotal evidence and do some kind of studies with our students. And like, are we teaching these things as effectively as we are, and, you know, find places where we're not and improve on those. So here are just some references in case folks want to look things up. And then I want to end with acknowledgements. This is teaching reproducibility in this program and in the undergrad space is at UBC a hugely collaborative effort. We work very closely together. We review a lot of each other's work. We do a lot of team teaching. And so, you know, all of these people have contributed to the opinion stated today. And so with that, I'll just end with questions.
Thanks a lot, Tiffany. Are there questions from the audience? And before should we I'll stop the recording.